Now I want to talk about cardinality and equivalent sets. So cardinality refers to how many elements are in a set. And I kind of mentioned this a little bit, like just in passing here or there. So now we're going to formally define it. So the cardinal number, or usually I think the word cardinality is used more often, is basically means how many elements are in a set. And it's also how many distinct elements are in a set, so meaning different elements. So we're not counting repeats. So typically when we write sets, we don't like to repeat our numbers anyway. It's not the standard form. But if you do have repeats, then when we're counting up how many elements, we don't count repeats. We just count each element once, each unique element. The notation we use is this. So if you see something like this, they're asking you to find how many elements are in that set. It's read n of a. And like I already mentioned, repeated numbers do not change the cardinality of a set. So if you have the same number repeated more than once, it doesn't matter. It doesn't affect the cardinality or how many elements there are. So here, find the cardinal number of each set. So first of all, I see I have 1, 2, 3, 4 elements in a set, and they're all distinct, right? I don't have any repeats. So n of a is 4. You kind of think of like n as number, right? The number of elements in A is 4. Here, I have the number 0 in my set. 0 is a number, it's not empty, right? So this is n of b equals 1. I have 1 element in that set. All right, here we have to think a little bit, right? We're going from 13 to 23 and we're counting by ones. So if you have to write things out, you can do that. You can just count. So I'm just going to kind of use my fingers. So I'm going to do 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So I'm at 11 elements. And the set is C. So n of C equals 11. Now, the last one is the empty set. And remember, you can write the empty set like this, or you can write it like this. The empty set has no elements. So what we can do, how do you write this? We can write this like this. N of the empty set is equal to 0. So the number of elements in any empty set is 0. Empty, or also called the null set, is 0, right? There are no elements. Now, with sets, and this is a little confusing, it's a little bit different than how we're used to think of it. The word equivalent and equal are not the same. Equivalent does not mean equality when we talk about sets. And it usually does, right? In the English language or in most math problems, like when we're solving equations or things like that, we use that word equivalent interchangeably with equal, but it's not true here. So set A is equivalent to set B, means that set A and B contain the same number of elements. So things are equivalent if we have that the number of elements in A is equal to the number of elements in B. They do not need to be the same kinds of elements. We just need to know that they have the same number of things. That's what equivalent means for sets. We can show this by counting, or we can even show this by using a diagram and like matching them, drawing arrows. So when we compare each element of set A with exactly one element of set B, we call this a one-to-one correspondence. Okay, so when you have that they have the same number of items, they have a one-to-one correspondence. So each element of A could be matched with an element of B. So these two sets are equivalent. Now they're very different sets, right? They have totally different elements, but let's write them out in roster notation. So for the first one, we see the set is A such that X is a vowel. So our vowels are A, E, I, O, U. And then for B, we have x such that x is a natural number and x is between 3 and 7, and they're both equality, so those n values are included. So 3, 4, 5, 6, 7. Now I can tell you that they are equivalent because the number of elements in A equals the number of elements in B, right? I have 1, 2, 3, 4, 5 elements in A and 1, 2, 3, 4, 5 elements in B. So they have the same number of items. The other way I can see that is by using arrows to pair up my elements. And you can do it like this. So I could say that like A matches to 3, E matches to 4, I matches to 5, O matches to 6, and U matches to 7. So every element in A pairs with an element in B. There's nothing left over. There's, no one's hanging out by themselves, right? So if everybody has a pair, then again, they are equivalent. And we also can say they have a one-to-one correspondence, right? So one element from here matches with one element from the other. If sets A and B can be placed in a one-to-one correspondence, then A and B are equivalent. So they do have the same number of items. If they cannot be placed in a one-to-one correspondence, so like matching them up, then they are not equivalent and they must have different cardinalities, a different number of elements. So let's say, for instance, that A was equal to the set 1, 2, 3, and B was equal to the set red, blue, green, and yellow, right? So I can see here that the cardinality of A is 3 and the cardinality of B is 4. They have different number of elements. So these are not equivalent, right? And they don't have a one-to-one correspondence. So if I try to match everything up, one buddy in group A gets one buddy in group B, what happens is poor yellow here doesn't have anybody to match with. So that is not a one-to-one correspondence. We do not have equivalency. Now, let's take this a little further and talk about sets being equivalent with a graph, because sometimes it's a little harder to see. I really like this example. So this is example 9 in your text. I just copied the picture here. It's a nice bar graph. And we see that the figure shows the top 5 impediments to academic performance for U.S. college students. So the top 5 issues that cause students to not do as well academically, or to cause that extra hurdle they have to jump over to do well academically. So the top issue is stress. And about 28% of those surveyed said that stress was an issue for them. Second was sleep problems at 20%. So about 20% of those people surveyed said that sleep problems were an issue. 19% said illness, 19% said anxiety, and about 14% said that work is an issue for them to doing well in school. So set A, we're going to let set A be the 5 impediments shown in the figure above. So I'm going to write this in roster notation to make it a little easier to see. So set A would be the categories of stress, sleep problems, illness, anxiety, and work. So those are the items for set A. Now set B would be the percentage of college students reporting each impediment. So those are your percentages. So I see 28. I see 20. I see 19. Now I see 19 again, but I don't need to repeat values in a set, and really I shouldn't. Sometimes people do, but it's sort of not simplified. So I'm not going to repeat my value of 19. And then I have 14. So notice that initially everything looks to be equal, right? Like a one-to-one correspondence here, right? Each bar has a different number, each category has a number, everything makes sense. But actually, these sets are not equivalent. If I think about the number of elements in set A, I have 5 distinct elements: stress, sleep, illness, anxiety, work. For B, I only have 4 distinct elements: 28, 20, 19, and 14. Remember, when you're doing cardinality, you're looking at distinct elements. So even if I wanted to write B, and I kind of made a mistake, and I was like, oh, I just put the 19 in there twice. Sure, but we don't count that 19 twice. It's not part of the cardinality. It just counts it once. So you only have 4 distinct items. So these are not equal. They cannot be equivalent. And when you try to set it up as a one-to-one correspondence, you know, stress went to 28, sleep problems went to 20. It's kind of hard to see, but illness went to 19, and anxiety also went to 19, right? And then work went to 14. So here, when I try to match these up, 2 of the items are going to the same 19, and I'm not getting that one-to-one correspondence, right? Each buddy needs to have one other buddy, not 2, so this doesn't work here. Okay. And then the last thing I want to talk about in this section are finite and infinite sets. Set A is finite if either the number of elements is 0, so it's the empty set, or the number of elements is a natural number. Sorry, let's just say cardinality. A set whose cardinality is not 0 or a natural number is called an infinite set. So infinite means infinity. It keeps going forever, right? So you can have sets that have an infinite amount of items. And a great example of an infinite set is the set of natural numbers, right? They're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I could keep counting forever. It never stops. So this is an infinite set. There's no way that I can give you a specific number that has how many items are in there. It goes on forever. And again, like I said, those dot dot dots means it keeps going. Because there's no end value afterwards, like I'm not ending at the number 10 or something, you assume that you keep going forever. So if a set keeps going on forever, then it's infinite. Anything else is finite, meaning that it has a specific amount of items, a specific number. Now, I will say too that in your text in chapter 2, in 2.1 and 2.2, they do go through more information about infinite sets, and there's symbols that we can use to count infinite sets. Again, we're not really counting because we know they're infinite, but there are additional symbols and notation that we can use, actually using Hebrew letters, excuse me, that do represent infinite sets. So if you want to check that out, it starts on page 59 in your text. You can do that on your own. I'm not going to stress that here because I don't think we need to go into that personally. As long as you can recognize that it's infinite, then that's good. But if you want to see more about infinite sets and how we can order them and kind of, we can't count them, but think about the idea of a count for infinite sets, then check out your text. All right, finally, equal sets. Now, the word equal means what you think it means. Set A and set B are equal if they have exactly the same elements. And again, regardless of order and possible repetitions. So we symbolize the equality of sets using the statement A and B. And if 2 sets are equal, they're also equivalent. So if something is equal, if 2 sets are equal, so if A and B are equal, we use what you're used to. So we can just write A equals B. So I'm going to make this equals instead here, instead of and. A equals B. So here are our 2 sets. Let's call this one set A. Let's call this one set B. So here we have the elements 4, 8, and 9. Here I have the elements 8, 9, and 4. Now, when we're talking about equality, it doesn't matter the order. So do they have the same elements? They both have a 4, they both have an 8, they both have a 9, and that's it. So they are, in fact, equal. This is true. These are equal sets. Here, they both have, we'll call this A and B, just kind of so we can talk about it. They both have a 1, they both have a 3, they both have a 5, but B has this extra 0, so they are not equal. This is not true. This is false. Now, it is really important that you distinguish between equal sets and equivalent sets, okay? So equivalent sets have the same number of elements. So the number of elements in A equals the number of elements in B. Equal sets have the same exact elements. So then we say A equals B. So you just want to be careful. Equivalent means that they have the same number of elements, right? Each set has 4 elements, whereas equal sets have the same exact elements. So not only do they have the same number of elements, but they're also exactly the same, right? Like they were here. So they both have 3 elements, but they're also exactly the same. So what we see is that if 2 sets are equal, then they are also equivalent, right? If they have the same exact elements, they must have the same number of elements, but the other is not true. We saw before that 2 sets can be equivalent, right, when we did the vowels and the numbers, but they're obviously not equal. They're very different.